All right. So, well, thank you.
One second, Igor.
Okay.
Okay. I think we're ready to go. Go ahead.
Awesome. Thank you, Rachel, and thank you to the organizers for having me here speak today. I would really love to be in Santa Barbara instead of connected remotely. My name is Igor Andreoni. I'm assistant professor at University of North Carolina at Chapel Hill. And today I would like to tell you about some challenges, some opportunities, some thoughts on transient follow-up in the era of Rubin Observatory. And if I was in person, I would probably ask you to raise your hand if you have ever heard the sentence, Rubin will generate up to 10 million alerts per night. I'm pretty sure all of you have heard it at least once. This is one number, but it already gives us an idea that we are now in a big data context. But I would like to give you a bit more of a visual impression of this big data context. What you see here is an image acquired with the ZTF camera, so the Zwicky Transient Facility. You can tell there are many, many sources there. There are a few dozens, even in that little blue square. This is fairly close to the galactic plane, so it's a little bit of cheating in that sense, but not too much. We're not right on the plane, but regardless, you can tell there are so many sources that we want to study, that we want to understand if they're changing in luminosity with time. But the catch is that this is only one quadrant of ZTF. ZTF is 47 square degrees, and there are 64 of these quadrants for each ZTF image. So every 30 seconds, 40 including overheads, that's the amount of data that we have to deal with, that we have to calibrate, process. We need to find transient and variable sources in, if that's the type of science that you're interested to, like in my case. And Rubin has a field of view a bit smaller than ZTF, but the depth that it can achieve is so much larger. And you can take one of your favorite sources, an example, say a type 1a supernova that you want to use as a standard candle, and you can wonder how far can I see it with ZTF or maybe another one of the wide field surveys currently online. And then you can wonder how far can I find it with Rubin. And once you adjust for the field of view, you can infer quite easily that the comoving volume ratio between the two, so the amount of space you're able to probe, is almost 10 times larger in the case of Rubin. I will not talk too much about the nitty-gritty details of the science, but just to present you one science case that is close to my heart that really needs not just discovery of sources, but their follow-up is absolutely critical. For example, I want to understand how much of our process element nucleosynthesis happens in the universe. One good way of doing it is through gravitational wave follow-up. So whenever we hear from the LIGO Virgo detectors that two neutron stars have merged, or a neutron star and a black hole perhaps, then we can basically stop everything we're doing and turn our telescopes to look at the highest probability regions in the sky, looking for transients, and hope that one of them is the true counterpart that then we can study and we can do science with. This was achieved successfully in 2017 with GW 170817. And we're still waiting for a second kilonova, this optical infrared counterpart, to be discovered associated with a gravitational wave event. Broadly speaking, the situation in which we are in is that we're given some maps, in this case represented by the more colorful regions, we identify transients, here marked with their TNS name, so the IAU-approved nomenclature. Then we need to understand if any of these is the real counterpart. That's why we need typically a bunch of observatories. This is not a job that people can easily do with one telescope. However, numbers are making us think. For the case of the second binary neutron star merger ever found, GW190425, you can tell from this histogram that out of the many candidates that were found, a few dozens, only several were followed up, either spectroscopically or photometrically or at other wavelengths. And just a few had a spectrum taken. And the reason why we need a spectrum in this case, in general, is pretty obvious. You need to know what the source is if you want to study it, if you want to include it in your sample. In this case, what we typically do is compare the spectrum we acquire with spectra of supernovae, for example, which are the most common contaminant among the extragalactic transients. But also we want to understand if the spectrum can resemble what we're looking for, a kilonova in this case. And if that's the case, and if we're lucky enough, like it was in GW17 then we can do the astrophysics directly with the spectra, with the light curve that we obtain, and then we can extend our knowledge, say, in cosmology. We can study the interior of neutron stars. We can really broaden the science we can address once we confirm what the counterpart is. Now, let me switch more to what the future of optical time domain service is like. Now, a lot of that future has the name of the Rubin Observatory. The observatory has already produced some very nice images. You can see here an example from the first look compilation of images that was produced. It is a big camera. It has 3.2 gigapixels. And the wide field of view of about 10 square degrees is very suitable to image the sky over and over again, so that if you're interested in transients and variable, you can do time domain astronomy. It will also reach extreme depth compared to present surveys in 6 different filters. That's why it's going to be so great for the static sky as well. And the resolution is also going to be good. Thanks to the, we're talking about a busy field. This is an example of a crowded field observed by Rubin, once again in view of the first look release of images. So when you have a big telescope like Rubin, which is equivalent to a 6-meter class telescope, the sensitive detectors, you can go very deep, which is good, obviously, because it can allow us to go the distance. I think this plot was produced before the different coating that was decided to be adopted for the mirrors, but more or less you can tell that the standard 30-second images will reach around 24 magnitudes of depth. This is a bit of an issue if you're interested in transients, such as a supernova. In this little movie that you're seeing now, see this map of the sky, and the dots that are appearing are supernovae that were found in this case by the ZTF survey, and that were classified as supernova. And different colors correspond to different classes of supernova. If our limiting magnitude for the survey is not as deep as Rubin, what you can do is some experiments that can be volume limited, that can be magnitude limited, but you can be complete in your spectroscopic analysis of transient candidates because they're reachable. They're reachable by other telescopes that are able to do spectroscopy. However, things are going to change dramatically when Ruby comes online. And we show you now a set of slides prepared by my colleague and friend, Armin Rest, which he basically analyzed how many transients, in this case, which percentage of events will be present in Rubin data for various limiting magnitudes. You can see how rapidly these curves increase and skyrocket around 23, almost 24 magnitudes. And these colorful patches that you see correspond to the sensitivity we may expect to be reachable by telescope of different aperture classes. So the first one, 1 to 2 meter class, maybe you can push to 20th magnitude. I slightly disagree. You can really do that, at least not in a very small amount of time. But if you observe for 1 hour, an hour and a half, this becomes doable. Then you can push towards the 4-meter class telescopes that can reach 22nd magnitude. That's very faint for current state of transient astronomy. And you really need big dishes, just Keck, Gemini, Subaru, VLT, to be able to observe transients that are most of the transients that Rubin will find. And the problem is that here, you can assume that you have all the time in the world and you have an infinite number of 8-meter class telescopes if you want to get 100% of the wide, fast, deep survey transients. However, realistically, we can get much less than 1% of these transients because we don't have an infinite number of telescopes and we don't have an infinite amount of telescope time. With 4-meter class telescopes, we can do maybe 30% of these, 77% of the amount of available transients, but ultimately just maybe 1 in 3 will actually be observable in the magnitude range of interest. You can do photometry instead. Why doing spectroscopy? Spectroscopy is by far the best tool to identify what a transient class is, but also you want to study their properties. You want to study which elements are present in the ejecta and how they evolve. Photometry can get you only that far, but of course, then we can get more completeness wherever we would be able to do extensive photometric follow-up. But once again, especially the largest telescopes are quite rarely used for purely photometric characterization as opposed to spectroscopy. In general, whenever a transient is found, it means that the source is found to be varying in flux compared to a template. So the comparison of the two, of the new science with the reference image, resulting in a residual in the subtraction, that's what's going to tell the system, tell the software that a change happened, maybe a transient source occurred, and this information will be packaged up into alerts. An alert ultimately is a JSON file that will include information of when, where, and by how much a transient has changed, a source has changed its luminosity. Rubin alerts will be public. So expect big requests, many observatories from the community, exactly because people from every continent, no matter the data rights that they have, will be able to access the alert packets. And let's go back for a second to the big data context. Let's not call it a problem because now it's just the world we live in. So ZTF produces, just for comparison, produces around 300,000 alerts in a median night. Rubin, we said, will be up to 10 million. There are other facilities coming online, which also will contribute with several million alerts per night. But also you have to keep in mind, there is a wealth of new telescopes and new instruments that are being built and will start operating soon at other wavelengths. Those include ultrasat and UVEX in the ultraviolet, for example, some X-ray telescopes, and we expect billions of new sources to be found in the radio when the SA2000 comes online. So just to keep in mind, why do we want to keep doing a good job with follow-up of transients? Is because we want to go from an unmanageable cosmic stream down to a selection of few candidates, and thanks to follow-up observation, ultimately do the science. And we're pretty lucky that some of these telescopes that will be key for the follow-up of Rubin sources are essentially co-located with the Rubin telescope. Those include Gemini, SOAR, Chile, more broadly, have a great deal of telescope that will be devoted for a good part to the follow-up of Rubin static sources and transit variables. But I encourage you to keep an eye on some instruments that are, some are currently operational already, some are being built or being deployed, that will be able to spectroscopically characterize thousands of sources at once using massively multiplex spectroscopy and fiber technology. Those include DESI, Foremost, and the PSF spectrograph that is mounted on the Subaru telescope. Interfacing between these observatories and the current facilities, I think, will be key in the future. In terms of survey strategy, that's been optimized over the years in an iterative process with feedback given by the community and then implemented in the simulated strategies by the Rubin project. And now I think we got to a pretty final version. In particular, there will be some trick, essentially, that will allow Rubin to observe some part of the sky at a higher cadence, which is suitable for the study of many transients by employing a rolling cadence. This means that the sky will be divided in stripes in declination that will be observed preferentially in 1 year, 1 season, and then the following year you will see a swap. So the more highly imaged region of the sky will be less imaged the following year, and vice versa. So this way, at the end of the 10-year survey, we may expect uniformity in the imaging of the footprint, but we will also have a higher cadence suitable for the study of transients and variables. And on top of that, we may hope to see some patches distributed along the galactic plane with more visits than what's currently planned in most of the footprint, so that there could be a better study of star-forming regions, of dark objects via microlensing, and that we can have a better characterization of the structure and the objects that are included in our Milky Way galaxy. On top of the standard surveys, there will be a target of opportunity program for Rubin. This means that in some exceptional cases, the regular survey operations will stop, and instead the telescope will go tile some regions of the sky where we may expect to find, for example, multi-messenger sources or some type of solar system objects, such as the potentially hazardous asteroids that may hit the Earth. So we will take advantage of the wide field capabilities of Rubin to be able to get where almost no other telescopes in the world can, in terms of probing very large regions at an exceptional depth and go do the science that you can only achieve when you're interrupting operations and triggering a target of opportunity set of pointings. Rubin is here. We saw, I think all of us, the beautiful first look images. I think many people in the call maybe have played around with the first data preview, for which data acquired with the commissioning camera were made available for everyone to make discovery with. And there are transients in those data as well. And what I heard is also that the brokers are already receiving alerts from Rubin so that they can check if the systems work properly and get ready for when the number of alerts will ramp up with the beginning of Rubin LSST. Let me point you to this paper led by my postdoc, Jim Freeben, here at UNC, in which we present a first set of transients that were identified, reported, and photometrically classified using DP1 Rubin data. I think the most exciting part here is Rubin is actually delivering, and from what we could tell from that little patch of sky that was analyzed is that it's performing well as expected for transient detection, and we can already find new transient in Rubin data. In the final minutes, I would like to share a few thoughts on what we need for the follow-up of transients and variables in the year of Rubin. I think ultimately we need a combination of very human decisions. They can be high level, like from basically observatory directors or federal agencies and funding agencies in general, some community level decisions. But a lot of what we need is software, from the scheduling all the way to the data reduction. Let's say some of the high level decisions I would like to see happen more and more, because in some cases, like in the case of Gemini already happening, is to have some dedicated observing time for the dynamic sky in the year of Rubin with the largest mirrors that we have available. Ideally funding for doing the science, that's always nice to keep us afloat. And some people are, myself including, are wondering whether we can establish some ways to also give dedicated fundings whenever proposals for observations from the ground are approved, similarly to what happens from space. The observing scheduling has been developed by many groups for many years. I think LCO is probably one of the most refined of such tools for scheduling observations. Something I love about it is that it can be largely done via APIs, which can make all the submission of requests and the retrieval of information fully automatic. We want it to be robust against telescope constraints and any other issues. It has to be dynamic to accommodate various types of requests. Potentially, the highest priority target should be observed. I think that's also where, in some cases, for various type of queues, this is one aspect that can be improved. So maybe have more interaction with the users to know your likelihood of the transient being observed. For example, so based on how busy the schedule is, quite simply. Multi-telescope optimization is something I think is going to be absolutely crucial in the future. The APIs and the automation does help that. Once again, LCO and other type of system are very good at managing that within the network. I think we should do more outside the networks, having various networks easily talk to each other. And understand how we can optimize observations that way. When it comes to data reduction, of course, we want to rapidly get the raw data it sounds obvious, but with some telescope, when you do classical observing, for example, that's not a very straightforward process. So in general, I think we need to move more and more towards automated copying of the data to databases that we can once again query purely using APIs. Pipelines will be key here. We obviously would like them to be free, open source. Some are still in IDL, which I personally love IDL. I did my PhD coding in IDL, but it's very expensive. And we really should move away from that and embrace Python possibly for all our pipeline. Easy to install, rapid. Of course, for some science cases, this is really key, like the one I told you about for the follow-up of gradation waves. It's great when pipelines are maintained and supported. And these, I think, are the ones that get more pull of the community. And if I can make maybe a small request to the people out there, having GUIs that can allow you to tweak when you do spectroscopy, of course, I'm talking about here, the aperture for the extraction and possibly also be able to handle the background in a dynamic way would be very appreciated. And at community level, we need to form and build and nurture community. That's of paramount importance. But there are some aspects that I think, especially in the field of transients, we can just keep improving upon. I think now almost every group are making their classification spectra public. It's really great to see that happen. I think this can be further pushed in the future. If you don't want to collaborate with everyone, it's totally okay, even if collaborations are available. But at very least, I would like to see more and more coordination moving forward, just to be practical, to optimize and do better and more science, everyone. And maybe even get to a point in which we can share our plans for which transient we would like to classify so that people can adjust their schedule accordingly. I mentioned automation many, many times now. I love automation. I need automation to do my science. But are we sure we're not creating another problem? I see with my students and postdoc, in 2 hours, I can give them some basics of photometry and spectroscopy, and then they can do projects almost end-to-end without knowing much more because of these wonderful software tools that are now available. But is that really what we want to, especially for the new generation, to have them so far away from the data? And I don't really know what a solution is for this problem, but it's growing. And I realized that, especially talking to the more junior people when, for example, at the RCW, the Rubin Community Workshop, and in other cases in which the Rubin community in particular comes together. But of course, there are many other skills that are needed to do science with Rubin that especially the youngest generations are so good at. And I think we will need to strike the right balance. So I will just conclude here, just sharing one more opinion, that the success in the Rubin era, I think, will rely on probably an equal combination of software, including all the new AI tools, astrophysical knowledge that can inform us on how to make better decisions, optimize our filtering of transients, and decide what to do with our telescopes, and hopefully some wise community decisions. And thank you for listening to me today.
Thank you very much for joining us, Igor. That was a really excellent summary. And you really identified all of the areas of development that we really need. I apologize for a little late start to this session. So in the interest of time, I'd like to move on to the next talk. And if anybody has any questions for Igor, then please reach out to him via the Slack channel. Igor, thank you once again.
Thank you, Rach, and everyone.
Okay, well, exciting. Yeah, hey, I'm Andy Howell at Las Cumbres Observatory, UC Santa Barbara. I'm also PI of the Global Supernova Project and co-PI of the Global Kilonova Project. And for the next 6 months or so, I'm still on the board of Gemini. So if you have concerns about that stuff, happy to hear it. All right. So, okay. First, we'll talk about, we're in this new era of transient discovery, and everybody's talking about Rubin, which is appropriate because it's so amazing. But there are other ways to trigger transient follow-up, and the science we get out really depends on the way we trigger our observations. So here on the left, it's just a bunch of different wavelengths, and then even gravitational wave and neutrino triggers. And depending on each way, this is just an example facility. In the second column, we see different things coming out, and we have different time scales that we have to react to those triggers, and then that affects, we're finding new types of things we haven't seen before when we find new ways of triggering things. And then we have to be reactive and follow up, and so we have to be very quick in some of these cases to get on something and then follow things for long periods of time. Since I don't have time to talk about all of those, I'm just going to take kilonovae, gravitational wave events as like an example case because it drives a lot of our the decisions we have to make for infrastructure because it's so demanding. So, for example, we get these alerts within seconds of this thing happening from LIGO, Virgo, Cagra, when the neutron stars are spiraling into each other or the black holes. Then we have a gamma ray burst. And in fact, then we have electromagnetic follow-up across the entire spectrum. So then we have to, marshal all of the resources astronomy has to offer in looking at these things. And if we miss some part of this, we miss some key part of the physics that we don't understand, which we did in the only kilonova that we've had so far. So one of the most important things for finding some kilonova is, LIGO gives us some error region on the sky, some big banana or something. And then we have to go and search that area to try to find the actual kilonova. And we've probably screwed that up in the past. So for GW 170817, the only one where we actually have seen something, it was only 40 square degrees, not that hard to tile. But there are other cases where it's much bigger. So for example, 190425, some areas of that big region were searched more than 100 times, while other areas weren't searched at all, because everybody's just going to the highest probability region and not looking everywhere. So an area equivalent to 100% of the localization was observed within a few hours, but and in 5 days, people searched basically 70,000 square degrees, greater than 7 times the localization. So according to some models, we could have found a kilonova there if we would have been better organized. And we'll talk about how to do that later. First, I'm going to sort of go through a lot of the problems we have with the current set of infrastructure, and then I'll talk about solutions after that. So another issue is that once we, in thousands of square degrees, we're going to find dozens of transients, maybe hundreds of transients. Then how do we tell which one is the kilonova? It's hard to do that with spectroscopy. It's hard to get that much spectra, but with photometry, we could do something else. So here's a plot from Araneda-Baltierra, which has photometry labeled by day in these numbers here. And if you plot, this is a change in G-band magnitude versus G minus R color, you can see regular supernovae are in this band here in black, but for the kilonova, it did this loop in this space. And so it changed in brightness, changed in color rapidly. So, but the problem with that event was it was only observable like an hour a night. So people at one facility may have one of those points. People at another facility have another point. Another facility have another point. And if we would rapidly share our data on what all these transients are, we have a better chance of finding the kilonova faster and then getting on it with these other resources like ultraviolet observations and so on that it takes to decode that physics. So we're missing science because we aren't sharing information effectively. Okay, so you're making Einstein sad. Okay, so we need better tools to share information more efficiently. Okay, so how does it work today? Well, we receive some text alert, okay, and it's getting slightly better, but a lot of the alerts that we receive are just plain text, hard to parse. okay, and we maybe even get an alert on our phone, and then we freak out for a second. Okay, it really does take a little bit of time. I've been on the top of a mountain, and get this alert, and then we all call each other on a phone or Slack messages or whatever else. Then we have to say, geez, what can I observe with this thing? What resources are available? To go look at a bunch of websites and figure out what's around. Go and fill out phase 2 things, which are these elaborate GUIs often, and that can take like 30 minutes just to put the observations into the telescope, which is time being wasted that the information is going away. Then you go and look up other resources available, talk to your friends, make collaborations. Again, all the time wasting time. And then, once you get the data, you have to go and download it from an archive and reduce it yourself, which takes time. And then, often write a text-based circular to tell people the results of this without actually sharing the results yourself. So all of this is inefficient and not the right way to do it. What we want in the future is something more like this. We receive some alert, and the telescope automatically receives some machine readable thing, negotiates priorities and data access, and just starts observing. Like take the slow humans out of the loop. Automatically have the data reduce and instantly be made available to the community, and then machines and humans make inferences based on available data and repeat, so that instead of us meat computers slowing everything down, things are actually just happening. This is just a simplified flowchart for how it sort of works, but you could draw this in a lot of different ways. So we have surveys finding things, and then it's communicating through some infrastructure. I'll talk about hopscotch in a second, but there are other ways of doing it. We get things filtered by brokers from this bigger data stream down to something smaller. Then we have some decision making and information gathering, deciding what targets to observe. I'll talk about brokers, treasure map, target toms, resource availability, and so on. We make the observations, and those might be robotic or some other ways. We like to use APIs and Eon and things like that to make this more efficient. We do some data reduction. Often now that's happening in the cloud, and we have pipelines in data lakes and things like that. Then we make some inference, sometimes using machine learning and other tools, and then we hopefully put that information back into some flow so that we can more efficiently make decisions with all available information. Okay, Igor already did a good job of talking about Rubin. I thought it was criminal not to have a slide about Rubin, so here it is. Basically, it's another way of surveying things, and we may find, well, we'll find all manner of transients, but maybe the next kilonova won't come from LIGO. Maybe it will come from Rubin, although probably not, since it doesn't come back in the same filter that often. And so for most of the sky, will come back, say, every 7 days or so in the same filter, which is not even enough to do most supernova science. So just keep in mind that to get the most out of physics, it's hard to do it with 24th magnitude objects. We get the most of the physics with 17th magnitude things, and so there's still going to be a market for small telescopes and alerting on things, observing things much faster than Rubin can do, and then getting data from that. Okay, we've just touched on brokers. So of course brokers take this big data stream and filter it. And so we have a lot of tools you can put in your broker to say, give me all the targets where the G band is changing rapidly and so on. So that's great, but there are some things that we don't have really figured out with brokers yet. So for example, okay, so this is brokers don't allow salmon. Okay, what does that mean? Well, okay, this is a race called the Beta Breakers in San Francisco, where you run across the peninsula, but some people run the race in reverse, dressed in salmon outfits. Okay, so the point is they go upstream, right? And so brokers are great at filtering the downstream data, but we don't have a good way of sending information upstream to the brokers that is centralized, so that we can all take and synthesize our data from a bunch of different telescopes to make better inferences about what's going on. This is a big problem that we really need to solve. Okay, another issue is resource availability. So, right now you say, what instruments are on Keck at the moment, and who's observing? And you have to go look at a website, and every telescope has a different website that tells you what they're doing. Some don't tell you at all. And you have to go and just check things everywhere. And it may be hundreds of places you have to check, again, while the kilonova clock is ticking away. So that's incredibly inefficient, and we need to do something about that, and we're trying to. Okay, another way we're getting data these days is through a TOM, a Target and Observation Manager. So some examples are the Supernova Exchange. That's ours for our project, but there's plenty of other examples that weren't made with the TOM toolkit. This is our old version of the Supernova Exchange that was not made with the TOM toolkit, and that's because I'm still going through the problems, not the solution part. But there are other ones called the Sky Portal, Easy Peasy, and so on that were made with totally different infrastructure. But these things generally organize information about a target. They have some kind of automated data reduction, tools for visualizing the data, tools for communicating and organizing follow-up and coordinating papers, and then often requesting data from telescopes through some API. So here you'll see supernova data we're gathering from LCO. It's being automatically reduced and plotted on this light curve. The spectra come up over here. Up there's a chat between people about what's going on with this thing. We have visibility at different telescopes and so on. But one problem is that TOMs are often one-off, like people just program it like a separate thing like Sky Portal or Easy Peasy. And then they require a lot of upkeep, and they often don't talk to each other. All right. Another issue in this whole space is data retrieval and reduction. We often have to go to archives, and not all astronomy archives are in one place. And then the astronomy archives generally don't talk to each other. And then data reduction is often a manual process requiring humans in the loop. So you have to know where to go to get your data, go and click a lot of buttons often to go get it, and then do that many times. There are such things as data lakes, where you basically you have a data set that's too big to download on your own computer, and so you have to work with it in the cloud. But the problem there is that archives are distributed. There's not one place. So you have to then download some data, then maybe re-upload it to some data lake if you're going to use that data in conjunction with other data. But there's no easy way to do that. And often things are distributed in different clouds like Amazon Web Services or Google or Microsoft Azure, and these things don't talk to each other effectively. And then our automated data reduction pipelines are pretty primitive. And for example, there aren't that many good general purpose tools for doing spectroscopy in Python, for example. So we need more Python-based platforms for accessing and analyzing cloud-based archives. And there are some things like Noir Labs Data Lab, but it's still not all the functionality is there. All right, so then the next problem I want to talk about is messaging. How do we communicate information to each other? Often we're wordy creatures, and in the past we just wrote notes to each other based on this archaic stuff that was invented in the telegraph era. But then there are, for example, GCN circulars where people write text things. There are GCN notices that people use to communicate things in a machine readable format, but then it's not human readable. And so that's tricky. That's typically meant that people write down the magnitudes of a kilonova in text, and that's not the ideal thing for just immediately parsing information. We have the transient name server that's used in like the supernova world, for example, to say, hey, here is a supernova. And that's effective in getting a name of a supernova and saying, say, the first magnitude it was discovered at or the first spectrum that's taken. But people don't then share other photometry or spectra, which we might need to do if we're going to efficiently classify something, like that first plot, the second plot I showed. There's astronomers' telegrams, but the community has largely abandoned that because it's just a bunch of text and it's run by a dictator. Then there's the brokers, which is a sort of more modern way to do it, but it's not everything goes through a broker. Right now, only ZTF thinks not every survey sends something through a broker. So again, information is scattered around, and there's no way to feed the information back into there. So in the messaging tools that we have right now, some things have high latency for the first GW event. Some people weren't even getting the GCNs till 20 or 30 minutes after somebody sent them. There's single point failures, like people forgot their password, or the person running the GCNs is not always available and has to manually add people, and so on. A lot of things are not machine readable. Information is scattered in many places, and some information is just never distributed at all because it hasn't been a cultural norm to say send all your photometry to all your colleagues. So we have this situation where we have information coming from LIGO, Virgo, Cagra, say, for example, and then they would report that to the GCNs. Then you might be at ZTF or something and see that, start surveying this guy, maybe report back some targets to GCNs. I haven't talked about treasure map yet, but I will. It's a place where you can report where you're pointing the telescopes. Hopefully you send where you're going to point your telescopes to the treasure map. Then maybe you're running your ZTF observations off of some kind of TOM. You then make observations at a telescope at an observatory using your TOM. You may trigger follow-up observations, report those back to your TOM. Hopefully you report those extra observations back to the treasure map. And then if you find some things, report it back to the GCN. Then you report things over to the transient name server to say what you got, and so on. And then maybe you even make space-based observations and then report those back to the GCN. So this is complicated, and there's a lot of APIs and interfaces involved and a lot of manual steps in this process. But we can do better. Okay, so now I want to talk about some of the solutions that we're working on, and there will be talks on a lot of these things in the rest of these sessions. So one is the treasure map. This is a collaboration between a lot of us that you see written up here. And what that is it's a visualization on the sky of some underlying survey, but then you will have the error region reported by LVK, and then you report where you're pointing your telescopes, were you planning to and have pointed your telescopes, so that we can more efficiently cover this localization region to cover that first problem that I talked about. And you can do all kinds of advanced stuff with this, but I'll leave that to the actual talk on treasure map. Next is Eon. Rachel's already talked about this, so I think I won't talk about this very much, but basically it's a way of encouraging observatories to more automate their process of getting observations efficiently. We at LCO have robotic telescopes, and so we want to make that roboticization more common and have APIs triggering things. So we have an observatory control system that is open source, and we want to encourage other observatories to adopt these same kinds of things so that, like, say, the triggering mechanism of a telescope is much more standardized. So I think there's going to be a talk on that too. The TOM toolkit. So I mentioned building a TOM. They're often done in a one-off way, but we started doing our own TOMs in one-off ways. We realized we should just make centralized tools and have that available to the community. So that's another great success story. And we'll have talks related to this kind of thing. So I won't belabor this point, but basically, why keep reinventing the wheel? We can all contribute to making the same modules that we all use together. All right, so some of the things I'm going to talk about next are results of SIMA, the Scalable Cyber Infrastructure for Multi-Messenger Astrophysics. It's a group I'm a part of, where the NSF realized there was a need to make new tools for these time domain ecosystems, and sort of convene this group of people from lots of MMA things like LIGO, IceCube, computing centers, astronomers, to work together to make some of these tools. You can go to sima.org and see more about that. One of them that we're making right now is called Heroic, and we'll have a talk about this as well. That's trying to put together information about what resources are available in one centralized place. Right now, it's been funded to do Las Cumbres Observatory and some Noir Lab facilities, but of course, we want to work with people from anywhere to say, hey, here's what resources are available. So you would put in, say, a target date range, and then you'll see over here, well, here are the facilities that could observe this, what their status is, what instruments are available. There's maps on the world that show this. They show observability, all these kinds of things. And this is run by an API and has access to the observing databases at each institution. So it would be great if we can get all observatories doing something like this. In terms of improving messaging, SIMA has made a thing called Hopscotch, which is it's a Kafka-based system, which basically is just a very robust messaging system that's used by lots of corporations and Twitter and all kinds of stuff like that. It's a publish and subscribe pub/sub model, so you could subscribe to only the information you want. And this alleviates that problem of why we only ever send out discovery magnitudes in one spectrum, is because there's just a stream that's always coming and nobody wants to overwhelm anybody. But if you have a bunch of these topics you can publish to, you can publish anything. You can publish all your data that you're getting from your observatory on one of these streams, and people can just subscribe to the piece they want. And it carries all existing astronomical messages that we can. It carries GCN notices and circulars. We would like to carry more transient name server messages, astronomers' telegrams, and things like that. But the goal is to increase machine readability of information. So Hopscotch has no priors on what information is carried. You could write a FITS file, a spectrum, photometry, whatever to a topic. But then the question is, how do you, well, before I get to that, I'll say this is in the cloud, and we have identity and access management tools so that you could log in with, you don't need a new account. You can just log in with your institutional account or your ORCID ID or Google or whatever else. Okay, so this Hopscotch is the basic Kafka thing with a bunch of layers of tools added on top, but it doesn't say, it's agnostic as to what the message structure is. But that can be a problem if you don't know what the message structure is, you don't know how to read it. So to solve that problem, we invented something called Hermes that just runs on top of Hopscotch. And that adds a graphical user interface so that you can see what the messages are, but also has structured data for sharing photometry and spectroscopy and so on, so that now you know exactly what the key value pairs are that you need to read to share data. So there will be a talk on Hopscotch and Hermes coming up, so I won't go through a lot of this, but I'll just say that there's one part of it that is, a message browser here where you pick a message, and it has integrated both the like GCNs plus LIGO alerts plus any message sent through Hermes or Hopscotch. Then over here you can read the message, but you can combine machine readability and human readability. So everything is parsed as some JSON table, the variables that you use. So for example, here is a way you would send a message. This is actually an older version of it, but you'll see the newer version later. You can upload your data in a table that is structured and then refer to those values down here when you write the message, and it's all encoded as a JSON. But you can also make it send it as a text if you want to send it to GCNs, and you can send something to the transient name servers simultaneously. So improving the efficiency here. So there is now more modern messaging that has incredibly low latency. We have some requirement to have unbelievably small downtime, and so it's robust. It's both human and machine readable. You can look in one place for all the messages that you might need to look for. And then, and then it's pub/sub, so you can distribute any message. Okay, so we're almost to a place where we've simplified that spaghetti diagram where everything can sort of communicate through one hub. And we're trying to minimize the number of places you have to go in some astronomical emergency and get data. Okay, but a lot of this, if we're starting to share, oh, I should say also with Hopscotch, there's a way to, because I can write all of my data to one topic, somebody else can then read that topic, and you can have private topics. So now between a collaboration, you have a Tom built with a different system than my Tom, our light curves can just show up on each other's Toms, for example. Okay, but this does create a new problem, and that is that you might say, well, I don't want everybody to be sharing all of my data in real time because I want to just take everybody else's data and then put it with my data, and then I'll be the one to make the discovery. And so that prohibits the sharing of information, or somebody else might publish your data and get all the fame and glory. So I think, you know, but then that causes people to hoard their data, and then we don't find the Kilonova better, and everybody loses. Okay, so we need something in between where people can share data that's preliminary data publicly, but still get credit for it. And so I think the solution is some data license, so that when you share data, it explains how it can be used, like software licenses. So, for example, you can use this data for planning purposes and inferences, but if you want to publish it, you have to ask me, or I have to be on the paper. So this could just be a simple flag sent with the data, but we culturally, as astronomers, have to agree to support something like this. And this is incredibly easy to implement. It's just that we have to do the social work to make it happen. All right, so in summary, we have new communication infrastructure and software tools. We need them to make to better exploit the potential of these incredible hardware facilities that we've made, and we're making improvements in every step of this process. So, for example, EON for streamlining triggering, Treasure Map for finding targets, Heroic for resource availability, the Tom Toolkit for data reduction and analysis, Telescope triggering, Hopscotch and Hermes for messaging. And many of these things are built to work together. So LCO has a hand in almost everything maybe everything I mentioned. But then they're somewhat built to work together, but we can improve a lot of that. And once we establish some new thing, it's important that it sort of become a standard, so that everybody doesn't start just making their own version of something and we have proliferation starts to abound again. Some problems are still unsolved, especially data lakes and archive compatibility, and those, we've thought about solving those. We've proposed solutions to solve those, but they're expensive and difficult, and they haven't been taken up by the funding agencies yet. Even Treasure Map, it took us, I don't know, 4 or 5 years of proposing for funding to get that funded in one NSF grant. So multi-messenger astrophysics is a useful driver because it has some of the most stringent requirements, but these tools we are making flexible enough to be used in all areas of transient astronomy, and that's very important for their uptake and everything else. We want to leave the era of just making a one-off tool for, say, supernova research, and have something that is more compatible to all kinds of transients discovered by Rubin, because some of the time when we start observing a transient, we won't know what it is, and then we'll get the data. We need to look at what it is and then share it with our colleagues more effectively. All right, I think that's it.
That's better. How about that? Okay, thank you very much, Andy. I'd like to invite our next speaker to come and get set up while we have time for one question. Yeah.
Hi, Daniel DeVos, FHT. You mentioned that the data is easy to get out of the TOM and get it to people, and I can understand that. And you also mentioned that it's hard to get it back in there. In your new system, do you solve this, and in what way do people use it?
So to share data between toms, you can write things to these hopscotch topics or using Hermes, and other people can read them. That solves the getting the information into your tom, which in your tom you may have filtered stuff down through a broker, and it's in your tom. Somebody else has information of their tom. If they agree to share it, it can show up in the same place, and you would run some algorithm in there. But it doesn't solve the problem of getting it back to the brokers, and that's the problem that I think we as a community have not figured out. I bring this up at every meeting, but
So
we've
why
never
would
figured
you
it
want to
out.
go get it back to the broker?
Well, the brokers in principle have more information because they have, say, contextual information about galaxies and other algorithms running that and other filters that other people in the community want to do.
Right.
My tom is my group's tom in general, and it may be a big collaboration. There's more than 200 people in the Global Supernova Project, but the broker is seen by a lot more people. So somehow we either need to merge the function of brokers and toms, or figure out a way for brokers to more effectively use this information. And one reason it's especially tricky is that, say, my observations might be in some Sloan filters, calibrated to some AB magnitudes, but somebody else has a different system and their filters are slightly different, and it's hard to synthesize that information.
Okay, thank you.
Time for another one or no?
Any other questions for Andy? Oh, sorry, over there, yes.
So you were saying that JSON notices were not human readable. Can you explain that? Because they are very similar to the text-based notices.
Yeah, what I mean is, okay, yes, I can sit down and look through a JSON and see what's going on. But I mean that people like to just be wordy and they say, last night we observed this field and it, did this thing and we found this new event and then we're going to observe it tomorrow or whatever. And so people don't put those in, say, GCN notices. For Heroic and Hermes, you'll see that you could just click on a tab and you can see the JSON view, you can see the text view, and you can see the words just right there so that you don't have to just look through a JSON.
Thank you. Okay.
Okay.
Okay, well, let's thank Andy one more time. Okay, so our next speaker is Fabián Araneda-Baltierra, and I apologize if I have messed that up, who's going to talk more about the heroic system that Andy just mentioned.
Okay. Hi. Hello, everyone. My name is Fabián. I'm from Chile, actually, and I work at the NCSA, the National Center of Supercomputing Applications. I think I have to hold this, otherwise you're not gonna hear. So yeah, I come from the University of Illinois at Urbana-Champaign. It was a long trip yesterday. And I'm gonna talk about Heroic, the hub-enabled real-time observatory information and coordination. So also, John Nation is joined me today to do the demo of the current status of Heroic. And this presentation is on behalf of the big team we have. Okay. For this. So what is Heroic? The idea behind Heroic is to join all the information we have regarding available observatory infrastructure and to provide that information. I think Andy drew the panorama very well, so we understand why tools like Heroic are necessary. But the core features of Heroic is display the status, current and planned status for the facilities. And we can follow up in the same place that status. Also, we can quickly filter those available infrastructure based on several things. We are going to see that in the demo later, and we can connect with other tools, for example, Tone, to make this simple and also more complex in terms of the scope. So why is it necessary? Yeah, because as Andy said, every second matters when we are talking about these kind of events. So having infrastructure available to operate and action, get into action, it's important. So multi-messenger events are rare and available. Okay? Those are some examples of, in the past, kind of important multi-messenger events that didn't went really well because we didn't have the infrastructure to support this. So we can have duplicated and coordinated observations, and we also need that researchers have visibility into who is observing what, where and when. So Heroic enabled this real-time sharing of plans and results across facilities. And the idea is to maximize the scientific return for limited telescope time. So Heroic is part of the SEMA family, and Andy talked about that. So SEMA ecosystem includes Hopscotch to submit the alerts, Hermes, the alert database, Blast, automatic real-time characterization of transient, and OpenMMA as a community. What are we adding with Heroic? Well, observatory coordination and facility telemetry. Also, we incorporate the federated identity via CA logon for security reasons. And the idea is strengthen the interoperability across the entire MMA network. This is a diagram of how are we organizing everything around this. And then, well, how Heroic works. So the idea is going from facility telemetry to actionable science in real time. So we are currently working with a secure, strong API, but we would also add Hopscotch, the streams as a communication between the facilities and Heroic itself. So what we're doing is aggregating status into a central database and then displaying that information for all the users. And that's important. It's not anyone who has a CA logon, valid access can use Heroic. So as I mentioned, we have the RESTful API and the Python Hub client. So we have summary tables, plots, and machine readable outputs that are usable. Oh, sorry. So, oh. What? Sorry. I think I'm missing a slide here. Okay, well, regarding the data design behind Heroic, extensible schema, JSON-based, which is adaptable for many instruments, it's machine readable. We are currently working with a Postgres SQL and a PostGIS database combo. The idea is to handle the GIS information the best possible way. We are currently working on access provided resources. We're using Indiana Jetstream 2 to run our development server and also our prod server. So yeah, I mean, in terms of technical deployment, that's the thing. It's open source. You can all check on the Heroic repository. And yeah, I think then the demo will probably show more things. So we are aiming to create impact into astronomy by the efficient coordination of efforts and resources, okay? So key reasons: prevents redundant follow-ups, enable coordinated campaigns, expand science, and make it accessible to small institutions, and integrate with other brokers. And I don't know why this is, okay, but here we have the demo I want to show. So currently the team is Curtis McCauley. He's our project manager. John Nation and me works developers, and Stephen Pothier, who is retiring, was part of the team doing the data population and the data testing. And I don't know where it's going to take me here. So okay, this is the current view of Heroic, and John is going to help us with the demonstration.
Okay, so when you first go to Heroic, okay. So when you first go to Heroic, you're met with this homepage that has this map showing all the telescopes that are on Heroic right now and kind of a overview of their status that you could zoom into and drill down into. And then on the left side, you have this like filter, a set of filters that you can populate out to get visibility for a certain target. So do you want to just fill out those filters really quick?
Sure. Okay. No.
So in date range, just pick next week, I guess. Yeah. And then target, say M11, maybe. M, yeah, sorry. Well, I guess there is an N11 somehow. Well,
It is.
okay. So yeah, you can see there's little check boxes at the top that say visibility and air mass. So it's done the calculation. It's gotten the visibility. All of those telescopes that are present on the map now have visibility. So some might have been filtered off. I'm not sure. If you go to the target visibility page, you can see the visibility and air mass values for the date range that you have selected and the target you have selected. You can also add some constraints like air mass and things on the left side, and you can also filter by telescope specifically. So yeah, if you want to go to a specific telescope page, it doesn't really matter which one, just as a demonstration. These are all the telescopes. Again, these are filtered by your visibility. And this shows your visibility for your target as well, along with the telescope status. So this particular telescope is available currently, so it's projected to be available into the future. And the visibility overlaid there is the little purple boxes. We also can take in future visibility, like planned changes or future status changes. We don't have any pre-populated here for status or capability changes, but they would show up here and they would be factored into the visibility for the target on those telescopes in the future. If you switch to a date range in the past, like past week instead of future, instead of next week, yeah, then go to a telescope. Click on the orange one, maybe. Yeah. See if we can get a bad one. The red one, yeah. And then click on that. So yeah, now we can see we have status in the past for this telescope. And so all those like red bars are different status where it was unavailable for a different reason. Due to weather, I guess, in some cases. So yeah, I think that's most of what you can do here on the UI.
Yeah, and also regarding the authentication, as you mentioned here, this takes you to the CIA logon interface, so you can log in with your valid CIA logon. For example, then I can log in with my data of the university, which I'm not gonna do because it's gonna take time. I have to check on my phone also. But yeah, as long as you have a valid CIA logon identity, you can log in into Heroic. Yeah, and also as I mentioned, we have a very well documented API and I will share then the repositories in case you want to take a look. Yeah, thank you.
Okay, I see we have a question already.
Yeah, this is Jamie Kenner. I'm here representing Swift and Across. I had a question about the authentication. What is available without authentication? Anything?
I mean, yeah, right. Well, you can see everything without authentication. Yeah.
Understand.
Yeah.
Okay, great. That's
Yeah.
good. Yeah, because one of the things I learned early on running an API for a telescope was that if we required people to have a login, it would actually stop people using it, right? Especially in like, say, I had an example where somebody wanted to use a Python, was writing their own Python package, and they wanted to have data from my API in their Python package, but they didn't want to have to deal with the authentication side of it. They just wanted the data. So yeah, if everything is just open, then that's great.
Yeah, whenever you authenticate via SCA login, you get your token, and with that token, you can start sending information. Yeah.
I have one other question. You mentioned in one of your slides about adding in like space-based missions into this, like Swift. On your air mass plot, do you just have like a line at 0 for a space-based telescope?
I don't know how we will handle that yet, because it's the next steps. So yeah, probably.
Yeah, it's just, I mean, you know, there's obviously ways of approaching this can be very space-based kind of like focused. Like I'm very focused on like space-based stuff. And, you know, when I'm working on stuff similar to this, we're trying to figure out how to be as agnostic as possible. And like seeing that air mass plot, I'm thinking to myself, well, the air mass plot for Hubble is obviously going to look a little different.
Yeah, we didn't show that off, but there is actually status for the sensitivities of LVK sensors in here, and if you do the visibility plot for that, it's actually a different plot that shows the sensitivities of those, not visibility. But yeah, so if another type of plot makes sense for space-based things, we can add that in that case.
Another thing just came to mind regarding the sort of like status of the different telescopes. That's some kind of live feed telling you whether the whether the telescope is able to observe or not. How do you get telescopes to agree to give you that information?
That's above my pay grade. Andy, how do they agree?
Well, I'm facing a similar question, you know, like with, for example, with a NASA telescope, if the telescope is offline, publicly announcing that has to go through NASA headquarters. So it's not really possible to get like a live feed telling you, oh, this, you know, the spacecraft's off, even though it could be off. Because there's levels of politics in that. And I imagine that's true for a lot of telescopes.
So for the heroic proposal, at least, we have buy-in from Noir Lab and LCO, and to push our telescope statuses to it, I'm not sure. Maybe Andy can speak to others.
Yeah, we always take a sort of build it and they will come approach, and so we that's the ones we could fund doing in the proposal. It was sort of set by a budget cap as well. How many people could we? So it takes some programming effort at a place. So we want to just encourage people to, once we have the system, we can tell them exactly how to write the API and hook in their database or whatever. We hope we can encourage people to do that. It may require different funding proposals, and in this case, go through NASA and maybe some politics. But in principle, there's not that much negativity and reporting. Your users want to know that your facility can be observed, otherwise they're getting phone calls. So it's just way easier if you just go to the webpage.
Yeah, that's fair. The one thing I would say is that if not having that information is a blocker, then that's a problem, because there will be people that will never want to tell you.
Then you can have the Glomar response, which is, I can neither confirm nor deny that this telescope is available.
Yeah, fair enough.
Since this is an online meeting, I'm going to interrupt on behalf of the Slack channel. There's a comment from Rob Seaman. It's a lot of Andy's talk overlaps with the original US VAO virtual observatory plans. Not to put too fine a point on it, but funding is needed, and losing funding, as the VAO did during the Great Recession, is an existential threat to many activities. Did you have a response to that?
Yes, of course, we're constantly thinking about that, and in some cases, we've had, to move resources from one place to another. Some of these things we've tried to deal with that by integrating them into, for example, how LIGO functions. So if LIGO is funded, we'll still keep some funding for some of these things. It's always going to be a problem, but you can't not do something because you might not have funding in the future.
That's fair. I think we have time for one more comment, and I saw you first. Sorry, Griffin.
Maybe Griffin and I have the same question. Yeah. So how should we? I'm Dave Sand. How should we use this? Is this something we should integrate into our TOM and, send out an API call and say, hey, is this telescope I have a program on green light right now? And if it is, then I order the observation on my TOM. Is that what this is kind of meant for? Is to ping the observatory? Is it on? Okay, now I could trigger?
Yeah, so we've actually talked about, Gautam Narayan, who is also PI, the SEMA part of this grant, really wants to have telescope triggering through heroic. And I argue that no, that's the function of TOMS. So we haven't fully figured out exactly how that will work. So that would be a good on-conference session or something. But we want to make this as interoperable with TOMS as possible. And maybe John has something to say about that.
Yeah, I think we would want a TOM integration where you can get the status through the TOM and then you submit through the TOM already. So
can you say how much of this is backed by APIs?
All of it is backed by APIs. So yeah.
Okay, thank you all very much. Please hold your any further questions till the break. Thanks a lot. And thank you, Fabian and John, very much.
Okay, great. I forgot to put an intro slide. Hi, I'm Moira Andrews. I'm a grad student at LCO. I work with Andy, going into my third year. And I'm going to talk to you guys a little bit about what Andy introduced, which is just our specific TOM, which is the supernova exchange, and a little bit on Hermes and hopscotch integration. This will also touch on the gravitational wave handling of the supernova exchange and just generally cover it. Now, I think a lot of us are pretty familiar with the supernova exchange, just knowing the group here, but for any of the uninitiated, this is our more modern version of the supernova exchange, SNEx 2, where it is based on the TOM toolkit. I'm getting confused. So we essentially have, it's built on the TOM, but it integrates a lot of the features that we had in our pre-TOM version. And that includes target creation. Currently, we do this manually, either through a TNS page or using just a manual target upload using the TOM form. And we also handle and schedule our LCO observations. So there's through the TOM toolkit, I'm sure there's some other talk that goes into more specifics about that, but we mostly just schedule through LCO, but there is SOAR capabilities of scheduling. And we also view and handle the management of our data. So it has kind of end-to-end of scheduling and managing the target creation and handling of the targets and follow-up, and then also just viewing and handling the data and distributing that. And I'll get into a bit more about the best path forward on distributing data for a collaboration of this size and collaborations using supernova data. We also can view the images, and then Andy touched on it, but there's the communication with users. And so if we start with just the target creation, we have the TNS page that I mentioned where you're able to just view the targets from TNS. You can see that air mass plot and check for visibility at the LCO sites. And then there's also just some the TOM toolkit form where you can fill out manually. And this can be automated. Some TOMs use a more automated approach to create targets. But for our needs, we vet targets before we create them, or we create them as we want to do follow-up observations, so we don't get flooded with everything. But it can be automated for other TOMs. And so if we go to a target page, just the landing page looks very similar to one that Andy showed, but you have this visibility plot, you have the comments to communicate if there's other data, if there's anything particularly interesting about this target. There's the images that we can reference, so you can take a look at them, all the output images. There's the alias names. So you have your TNS name up at the top, but then you have other names for other associations, other observatories and collaborations that are viewing the target, and that links to the transient name server page as well. And if you go down, this is where we're able to view our data. So we have our spectra on the right. I'm not going to go too much into all of the different pages and get really specific, just because I don't know how necessary that is. But we have our kind of more collaboration things, like who's writing a paper on this, how much data, what kind of data are they using. It has our photometry that you can also kind of investigate. That's just from our pipeline. And then we have our spectra on the right, and this is all reduced spectra. So this is the Floyd spectra that we observe. And then you can also, these are uploaded spectra from SOAR or any other observatories that within the collaboration were observed and uploaded onto the Supernova Exchange. And so while each of these target pages handle and display the data of each object, a question going off of this is, how is this data managed? Because not only does the collaboration use the data, but other collaborations might want data, especially at early times in the discovery, where we would want to be able to share this among each other. And so this is where we're talking about what Andy introduced, where we're introducing these different toms that would want to talk to each other. And so if we have the Supernova Exchange, if we have Saguaro and other toms or other non-toms that want to be able to share this data, you need to have permissions between each of them. I think everyone knows where I'm going to, but we have all these authentication and tokens they need to handle. And once you start introducing more and more of these target and observation managers that may or may not be in or out of the TOM ecosystem, it becomes more difficult to actually share the data because you need to handle all of these permissions properly. And not only that, if you're sharing outside of the collaboration, you'd want to make sure that you're not like going against permissions within just the collaboration data, public versus private. So all of this needs to be like handled properly. And the best way forward is using some third-party server like Hopscotch and Hermes to be able to solve this issue. So I'm going to breeze really quickly through this because Andy did a great job introducing this. But Hopscotch is the Kafka-based messaging service where you're able to send and subscribe to different topics that allow you to share data in a much more standardized format. And if we compare this to Hermes, where that's the front-end reader, the database that we're able to actually write all of these topics to and read them from, it allows this essentially middleman for that sharing circuit where we're able to then just write it and read it from just sharing all of our photometry, all of our spectra to maybe like a GSP private topic, where we're then able to share that amongst each other without having to worry about all of these different special API queries and all the different tokens and permissions required. So if we take a look at what Hermes looks like, this is a bit more of a modern version where we have like this filtering in the top left that I'll show an example of in a bit. And we have this, the text readable, the human readable on the right. And you can show the JSON, which I will show in a bit, where we have the machine readable version that has everything laid out, that has references that are easily parsable. But then also, if you prefer just being able to read it and like be like, oh, when was this observed, and have it be very wordy, that's totally doable all within this ecosystem. And so if we go back to our target page and we go over to the photometry tab, where we're looking at all of those photometric data points, we have, you know, the filter information, the magnitude information, all of this, and then we have this share over on the right. And so just for this example, I went through and I picked a few data points, and you scroll all the way down to the bottom and we have like a submission to Hermes form. And so I'm just putting in some text, I selected the data points, and then I click submit. And that's as easy as it is. And this is still a pretty manual format of submitting to Hermes. You can more automate it on the back end. But just for this example, just being able to be like, oh, I want to share these data points or all this data from this target, you can very easily do that within a TOM like the Supernova Exchange. And so if I go back over to Hermes, you can see here that the same text that I put, and I have the photometry for it. We have all the different target tables, so it was just one target, so that's all that's shared. The photometry table that includes the points, Notice here there's also the aliases. So if you have a different name internally, you can parse through that and query by the alias. It has all the data points and all that information, so I didn't have to copy paste anything, which would increase the amount of error that could propagate. And then this is the JSON that's actually sent through the API, and it has all that information in a more parsable format for machine readability. And so if we look at another example of this, that's more of a manual upload. So this is, we're looking at more of the like front end types of uploading to Hermes. So we had the uploading through the Supernova Exchange or a TOM, and then also you can just input them manually. So this is on the submit message form, and there's different views that you can go off of it, but it's a very clear submission form where you just fill everything out. You can put your notes. You can also validate it to be up for the transient name server. There's GCNs that are gone on here that Andy touched on. Yeah, and you can manually input your target information, or if you just have like, I observed this target at this RA and DEC, you can also just upload a CSV that helps with the kind of automating of at least this manual form. So if you don't have like a target and observation manager, but you just have data on, I observed these targets at this time, and this is the photometry, you're still able to interact with Hermes without needing that software infrastructure baseline that a TOM toolkit requires. Yeah, so you're giving all of your photometry information. You can manually give it in per target, so it doesn't only need to be one target for a Hermes message. You can send out multiple targets on it. It's just how you want to distribute the information and what kind of packet you want to be delivered to be ingested by someone else. And there's other ways of doing it. It's all parsed within Hermes. So this is an example with photometry, but you can also upload like all of my photometry and all of my spectra. And that will, like, since it's flagged differently, that still makes it equally machine readable, and it's all handled on the Hermes side, which makes it very compatible with batch uploads or just continuous uploads on the back end. And adding references for where the data is gotten or where it was used. And then you can add a message as well, or just any also key value pairs. So if you want to give more information, like maybe a license for the data or an email, you can include that just very easily through this extra key value pairs. And then you can give a like more wordy, verbose message that describes what the data is, where it was used maybe, how it was observed. So then it's more understandable instead of just a JSON file with a bunch of data and you don't really know where it came from. So this adds to the human readability of it. And what we're showing here in this example is you can also use like the form information, so you don't have to copy paste everything. And there's a preview and a help where you're able to learn how to actually, the syntax of what that looks like. But this helps with, you know, if you're copy and pasting all of your targets and all of their RAs and DECs and all of those magnitudes, you don't need to do that, which, you know, every time you copy and paste, that's an opportunity for error. So it reduces that by just having it be very parsable and machine readable. Yeah. Anyway, so this is just a simple form for it. I'm going to keep going forward because I think we're a bit over time and talk about non-localized events within the TOM toolkit and a little bit more of what Hermes allows on the Supernova Exchange. Yeah, so here's the full, I was showing it before, but the JSON file that is sent through the API. So this is the non-localized event page for the TOM toolkit. This is what the Supernova Exchange uses and any other TOMs that use non-localized events. So this might be familiar to many of you. But essentially you have all of the GraceDB information and the localization region all within the Supernova Exchange. And it's added to our page through the Hermes alerts. So we're able to get these ingestion alerts and these events powered through Hermes GCNs. And so if we go back to our Supernova Exchange page and we go to the GW events page, then we are able, oh wow, okay. we're able to see recent events and be able to very easily see that event details page. And so this one is just an example, but let me show one that has a little bit more information on it, at least more recently. This was back in 2024, 0422 ED. I think many of us are a little bit scarred by this, but that's okay. So we're able to see these alerts and these messages sent through it. And then if other things that we're able to view on the SNEx page is the galaxy information. And so this is where we're actually doing our observations. So the group here, we would observe individual galaxies instead of tiling. And so we rank our galaxies and we can very easily, this is where we have more like batch target creation and observations. So we can just submit the first 30 with given exposure times and filters and numbers of exposures. And through that, we're able to then see the galaxy images where we have just automated subtractions where we can see the triplets. And this allows us to like very easily parse through all of the data and like look for something a lot faster than in previous ways where we just kind of have to get lucky looking at the kilonova and knowing that it's there. And this is all powered by what Hermes was able to communicate through. Okay, so next, let's just talk about how this fits into the ecosystem. That bar is covering it, but it says current ecosystem. So essentially, the Hermes ecosystem mostly uses GCNs, but it has capabilities to communicate in between TOMs and other TOM-like services where you're managing observations of observatories. And it's a future thing of wanting to be able to talk through the transient name server. And while the TNS doesn't directly report to Hermes, it can report through TOMs that ingest directly from TNS, since their API is not complete enough as Hermes to give this very machine-readable format. Same thing with GCNs, where that allows that extra capability and functionality. And right now, they're like, this kind of solves that issue of having to go to many locations and have to talk Tom to Tom or, you know, collaboration to collaboration. This allows like that linking between all of them. So then we don't have to go to a million places and know a million passwords and know a million things to be able to share data amongst collaborators or even just intra-collaborators. And you're able to see it in a bunch of different formats that make it very easy for us to actually communicate with each other and make the data as efficient as possible. Okay. I'll leave this up as a question slide. I went really fast to try to save time, so I will take any questions and I'm happy to elaborate on anything going forward.
Okay, thank you very much, Moira. I appreciate it. In fact, we're perfectly on time. Is that a question at the back, Andy? Or are you stretching? You are, right? Okay. You're determined to make me walk as much as possible. Hang on a moment.
Can you just show the Tom to Tom sharing video if you have that in your talk?
The what?
The Tom to Tom sharing where the light curve shows up in the other Tom.
I don't have that video. I'm so sorry. I should have put that video in there. I'm so sorry, guys. That's a great video, though.
Well, okay, what it shows is I have a light curve in my Tom. I click share to Hermes. You look at the other Tom, and the light curve just shows up in the other Tom by sharing through Hermes.
Trust me, it looks so cool. Just imagine it.
We have one comment from, pardon me, Mark Gowell online. He says, how expandable is Hermes to other follow-up wavelengths, e.g. photometry, spectroscopy at millimeter, sub-millimeter possible?
So it literally just takes the photometry information. So I think it's very expandable, where you're just giving the filter information of what you're observing on and the unit information. So as long as that's clearly communicated when you're drafting the message, then it's very expandable to those other wavelengths. I think Andy has a comment about it.
Well, but the question was more about like radio and stuff, and so that's not it's not currently supported, and but we want to support that. So we're absolutely happy to get feedback from the community on exactly how to do that.
Yeah, it's always a working model. So, you know, anything that needs to be added to this to make it more functional with these other observatories and other types of data is always necessary to improve upon it.
And I'll notice we have a session dedicated to radio and submillimeter tomorrow, which this would be a great topic of conversation to pick up on. Are there any other questions for Moira at this moment? If not, let's thank Moira and all of the other speakers from today's session once more.